Welcome to a lesson with Dr. Powell. Let's look at an example where we define two functions via fiberblocks diagram for each one, but kind of in a fun way. The, the fibers won't look like boxes, yet we're going to use the same idea. So to define a function, really what you need is you need a partition of the domain into parts, and then you need to label each of those pieces with a codomain element. Now, the fiberblocks diagram just between those labels and the partition would give you a surjective function, a surjective because you'd hit all your labels. However, it is possible to have lots of unused labels. In fact, we're going to have lots of unused labels in our case, and that's just fine. But we can still define the function. For instance, for this one, why don't we just take the fibers to be circles centered at the origin? So, and if you like just the circular path right here. So if you take all circular paths, everywhere, and even just the origin itself as a circular path of radius 0, you would fill out the entire plane. And they partition the plane, one for each particular radius. So those are the different fibers. Great. So now we just need to, so instead of a box, like in a fiberblocks diagram, then we have what? Just we have a circular path. Okay, circular path, and all the points on the circular path are in one fiber. And we just need to label each of these circular paths, right? Just label each circle. How should we label it? Well, we need to label it with something in the codomain. So maybe an easy way to do this would be something like this. Why don't we just draw a straight line like this, starting from the origin with a slope of 1. So y equals x, but when x is greater than or equal to 0, so just in the first quadrant right there. And why don't we just look at the intersection of a fiber with that line and say that's its label. Its label is just the intersection of itself, the fiber, and this line right here. So I know where to send everything. So basically I pick any point in the plane, find the fiber it's in, and then whatever fiber, and then it's a circular path. I follow that circular path until I intersect it with this line, and boom, I know where to send it, and it's well-defined, a well-defined function in that particular way. Now, let's do this again for another function. All right, so why don't we take fibers that are parallel lines this time instead of concentric or circles that are filling out the plane, but here are just lines that all have the same slope. So lines of slope 1. So here, 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 and in between and everywhere else, it'll fill out the entire plane. Now we also need a way of labeling each fiber box, you could say, or each fiber needs a label in the codomain. So what we could do is we could just draw a line like this that passes through each fiber exactly once, just like this line right here passes through each fiber exactly once. And we just take the intersection of the fiber and this line, and we could say, hey, let's let that be the function. Now, of course, we could define this in another way. We could say, instead of using intersection, maybe we could say go to the intersection and then go back a unit length 1 or something like that. Fancy, but just for simplicity, let's just define the function to be the intersection with that. So we get a well-defined function. Take any point in the domain, you can find the straight line of that slope that you're in. Take that line down to this line, find the intersection, and that's the output. So it's a well-defined function. Now let's take a look at what it would look like if we compose these two functions. All right, what if we composed g and f? Now, what does that mean? That means you plug the result of one into the other. Well, you put any, and actually in this particular case, since the domain is R2, we should write this as x comma y, okay, because we need a coordinate pair coming into f here. So xy goes into f, and what does f do to it? Well, it outputs a point right here because all the labels, the set of labels is actually the range for the function. So notice that there's a lot of codomain elements that have not been used, right? They have empty fibers associated with them. Only the points on this line do. So that's the full range, which means, so if you plug in any point, you're going to get out something on this line. Now, this line has slope 1. Oh my goodness. Now notice everything on this line is in one fiber, meaning it's going to have one place to go. Where's it going to go? It's going to go to the intersection of this fiber with this line, which happens to be the origin, which means that the composition of these two functions is actually constant. You always output the same thing. You always outputs, and there needs to be an element of the final codomain, which is R2, needs to output 0, 0. Thanks for watching.